with anticipation of joy when he will.
That's something that the whole society needs, is more excellent, dedicated, hardworking, phenomenal, good with kids teachers. That's what we need. Okay, so let's go into them. Any questions about any of that? And where is it? Okay. So today we're going to be talking about experiments. So remember, so basically the arc of the class right now, first we talked about endogeneity. So when do we get bad estimates out of our regressions? We get bad estimates when we have omitted variables bias, when we have simultaneity problems, or when we have measurement error. And the measurement error is just basically, are you collecting the data in a way that is reliable? So that's one thing. But simultaneity and omitted variables bias are both addressed when we have an experiment. So why is that the case? Remember that when we have bias from omitted variables, what we're really saying is that the beta that we're able to estimate is partially the beta that we want to estimate, but it also has this bias term, which is the omitted variable effect on the outcome multiplied by the relationship between x1 and x2. That's the relationship between x1 and x2. So when we have an experiment, this delta is annihilated. It's zero because it's randomly assigned. Random assignment doesn't have any correlation with anything else in the world. So it's not that I could randomly assign Devin to get the cancer treatment and that random assignment is correlated with his education or his height or his family status or anything else, because assigning Devin to whatever the treatment was is totally random. So it's not correlated with anything. What that does is it makes sure that delta 1 is always 0. That's what the experiment does. So the bias term is 0. And so what we're left in with an experiment is that we are always estimating an effect that's actually our true beta 1. That's kind of the short version of today, is that experiments are going to solve the omitted variables problem or the simultaneity problem really well. So we've been thinking about differences and differences yesterday. The experiment is actually a place where we usually use differences and differences. So remember here, we're going to have some average value in the treated group before the treatment takes place, some average group of the outcome variable in the treatment group after the treatment takes place, and then the same for the control group. And we can use the values of this table to calculate beta naught, beta 1, beta 2, and beta 3. So we did that yesterday, and we can do that again. Maybe we'll do that again on Friday for part of our review. But this is definitely a good thing to become familiar with on the test. So I think if there's this is just something that we looked at recently that would be kind of like a good question. I give you this little table and I say, what's the beta 1? And you could calculate the beta 1 actually from this table right here. Okay. So when we are doing an experiment with a difference in difference, we see everybody before we randomly, the treatment takes place. And then, half of you are randomly assigned to an extra review period, and the other half of you are assigned to not be invited to the extra review period. And then we'll measure your understanding both before and after random assignment treatment takes place. Okay, so what is a randomized experiment? A randomized experiment is a study in which we randomly assign treatment to a subset of the population and measure the differences in outcomes between treated and control, the treated and the control group. So this is, I think you should kind of think back to just medicine. Medicine is where randomized control trials are really used. So we don't know if this new Tylenol is going to help reduce your headaches. We don't know if this new cough drop is going to shorten your cold. We don't know if hydroxychloroquine is going to reduce the severity of symptoms for COVID or the vaccine. So they did do, yeah, exactly. So they've done these nice experiments with the vaccine where they take 1,000 people and they randomly assign some of them to get the real vaccine and some of them get a vaccine of water. And then what they do is they check in every week. They test both groups every week to see if they have had COVID. And they can plot over time what fraction of the vaccinated and what fraction of the unvaccinated people have had COVID. So that's kind of like the paradigm in your mind. As an experiment is where we're randomly assigning two groups of people to different treatments. And then we usually evaluate the effects of an experiment using a difference in difference design. So it's basically the same as a policy evaluation, except that the treatment is truly random, that it's not correlated with anything else. Okay, so a lab experiment is kind of the medical example. We do some of these in economics too, actually. We'll sometimes, so my colleague, Robert Innes in the department does a lot of experiments in his classroom. So he'll take the kids and he'll randomly send them to two groups, and usually they are playing a game where they are told some extra information or they're primed to feel a certain way, and then they respond to questions. So economists are actually often using their classrooms as a lab. I don't do that to you because I don't know why. I'm not that, I don't really work on I don't really do this very often. I don't really do this kind of experiment. So oftentimes you're going to play a game with some sort of financial incentive. So often they'll vary the size of the financial incentive. So one great example of that we talked about in class a couple of days ago was the tax experiment. So this researcher at Harvard and at Penn, they had kids in a classroom basically, and they gave them a task and they said, usually it's something like, can you copy this over here? And they varied what they would pay kids for their work, and they varied the tax rate that the kids would pay on the money that they earned in the lab setting. So they were able to use this experimental setting to understand how the tax is affecting people's productivity. And typically these kind of experiments don't take very long. They take kind of an afternoon, and then the data are all collected and you can get to work right away. There's another kind of experiment that's not in a lab, and that's one of the reasons that people like it, is that the lab is kind of a synthetic setting. It's a setting that doesn't really seem that realistic to people. So if I took you in a lab and what they basically tend to find is that the research subjects in lab experiments tend to act differently, in part because they sometimes know what the professor is going for, and they tend to live into the professor's expectation for what they want to find. So the results are sometimes kind of embellishments of what you would find in a natural setting. So a field experiment is basically a way of taking the lab experiment into the real world. So you might go and do an experiment, like there's a famous experiment where they go to like, I can't remember if it was a car show or a gun show or something like that. And they gave people that came to the booth, they would say, here, you get a free Toblerone or you get a free mug. And that was randomly assigned. And then they say, would you rather have exchange the gift that I gave you for the other gift that was available? And what they found is that once you had gotten something in your hand, you didn't want to exchange it for the other thing, and the reason is that people have this thing called I'm missing the word. It's called prospect theory. It's this kind of like ancient part of your brain that wants to keep what you already have. And they think that this kind of made it so that you were very good at preserving the things that you already had. Yeah, so it's kind of you form a possession feeling for whatever's already in your possession. So you're less willing to trade it away. So these are administered in the real world. They're not administered in a lab. They're intended to not know that they're experiments. And then sometimes we do these a lot actually in developing countries. We'll go into different villages and we'll provide medicine or food or money or additional information. And then we'll collect information on how that, on the outcomes for those people or those towns. And these usually take many, many years. They're very expensive. They take years and years to collect the data and even just to get the money together to do that kind of thing. Okay. So why are experiments good? Let me give you the case for why experiments are nice. So first, if the assignment is actually random, and if our treatment and control groups are big enough, then the treatment and control groups will be balanced on observables. So that means if I'm randomly assigning this class to a 4 p.m. and a 6 p.m. review period, the average height of those two groups will be the same if the class is large, which is cool. What it also means is that the treatment and control groups will be balanced on unobservables. So if I'm randomly assigning you to a 4 p.m. and a 6 p.m. Review period, the average religiosity of those two groups will be the same. The average work ethic of those two groups will be the same. The average, like something I couldn't measure, like how prone you are to kill your wife or something like that, would be the same in the two groups. Okay, so because of that, we can safely assume that the two groups are identical, and therefore that they would have had the same outcome if not for treatment. So that's the whole logic of the randomized control trial is that the two groups are going to be identical in observables and unobservables because of random assignment. So what are the limitations? That's the upside of experiments. What's the downside of experiments? So the main thing is that many interesting questions can't be tested using an experiment. So for instance, I will never be permitted to randomly assign years of education to different kindergarten students, where I say, this kindergarten student will be allowed to have 12 years of education, and this kindergarten student will be allowed to have 8 years of education, and this kindergarten student will be allowed to have 16 years of education. It's a decision that's too important to be decided by Andrew Johnston. The other thing that makes it hard is that sometimes treatments are too expensive to study. So say we had a treatment of going to, let me think, what's a good example? Say we wanted to pay for 4 years of college for half of our study sample. Well, college, even if you're going to a public school like UC Merced, is very expensive. That's $100,000 treatment at least. So it'd be very expensive to run an experiment where I randomly assign half of 100 students to go to college and the other half pay for their college and the other half not. And then finally, lots of treatments would be illegal to randomly assign. So I can't randomly assign you to take crack cocaine, or I can't randomly assign you to be, another good example of this one, too important to be decided by researchers, is family structure. So I can't randomly assign some parents to get divorced and other parents to stay married. That's a decision that's just too big to be decided by a researcher. So what are some examples of these things that we really couldn't study with experiments? We can't randomly open some countries to trade and not others. It would just be impossible. We don't have countries have sovereignty. That means that they can make decisions for themselves. It's kind of actually an expression of democracy, that people's governments are responsible for the decisions within their borders. Another one is paying for people to attend college. Or that was accidentally the example I just gave. And it would be too expensive. And then what would be illegal? Making some people smoke and not others. So that would be bad. So then the final kind of criticism of experiments is a thing called external validity. So say I did a study among 100 college students at UC Merced. And then it was, we were randomly varying some little message. I said, you can do this. And then I found that you guys did a lot better on some sort of task after I told you that you could do it. So the problem is that might not scale up or work outside of the lab or experimental setting. So that's what external validity is would this result hold true if we performed it in a different setting? So what if instead of doing it at UC Merced, I did it in Nairobi? Or what if I did it in a high school in Appalachia? Or will we get the same results? And then many things don't scale up. So when you do them in a small setting, sometimes you get these big effects. But when you go and you do them in a larger setting, you don't get anything similar. So those are the main criticisms of experiments. So let me pause and take questions here. Yesenia, Warren, Stephanie, Noah, Manuel, Luis. Anything? Okay. Good so far. Sounds good. This is hopefully like the most easy of the slides. There's not a ton of math. So the econometrics is that randomization forms a treatment and a control group. We verify the randomization by checking to make sure that the observables in the treatment and the control group are the same or not very different. And then we do a regression, which will usually be a difference in difference. No worries. No worries. Secret messenger. No problem. Okay. So this is a great experiment that a woman called Esther Duflo did at MIT. And her colleague called Michael Kramer, who's now at University of Chicago, two phenomenal economists that won the Nobel Prize last year. I think it was last year. And so what they did was they went into African villages, African schools, and they dewormed the kids. So the kids get worms in their feet. It's a parasitic worm that's in their feet because the children walk through feces. So the feces that live and grow in, the worms that live and grow in the feces infect the kids' feet. So these parasites cause illness and other medical problems because the kids have bare feet and they're walking through poop. So what economists did is they tested the effect of giving children a deworming pill on their school attendance and future labor market outcomes. There were 532 school-aged children where the researchers conducted the study. And so they randomly assigned the deworming pill to 266 students, and they had 266 control students. And they collected data about each student's characteristics and then their test scores and their labor market participation, both before and after the experiment. So that's the design. They basically are going to take 500 kids. They're going to evenly divide them between some of the kids are going to get deworming medication, and some of the kids are going to just keep living as they were. And then we're going to measure whether the test scores in the treatment group is going to change. That's the primary outcome of interest in this study. So the first thing that we're going to do is we're going to check to make sure that randomization actually happened. So what we do is we look at the observables of the treatment group. So we might look at what fraction of the treatment group are girls and what fraction of the treatment group of the control group are girls, what fraction of the treatment group have high test scores and low test scores, and see that they're the same in both groups, the treatment and the control group. So this is just a check to make sure that we actually randomized our treatment. So how do we do it? We are going to calculate a t-statistic not going to ask you to do this on the test, but you basically have the difference in each observable, the average difference in average observables between the treatment group and the control group. And then you're going to divide by the standard error of that difference. And the number of degrees of freedom is the t-statistic from the smaller of the two groups. So that's one reason why we tend to make the groups equally sized when we're doing these, because the power is limited by the smaller group. So here's what we have. So look at we have a comparison of the treatment and control group of the before treatment variables for the deworming study. So what do we see in the treatment group? 51% of the treatment group are girls, and 50% of the control group are girls. And so we can do that little test where we're going to say 0.511 minus 0.502 divided by the standard error, which we don't have here, is going to be equal to some difference. And if we calculated that out, we would find the p-value would be 0.84. So that means that these are statistically the same. If it was a very small value like 0.001, that would mean that the two numbers are very different. So boys are just the ones that are not girls are boys. And so we're going to find exactly the same difference and exactly the same p-value. We can look and see if the age in the two groups are similar. So here we have the average age in the treatment group is 9.7 years. The average age in the control group is also 9.7 years, a very small difference. The number of absences before treatment, the treatment group has actually a little bit more absences, 1.5 day more absences than the control group, but these are also not statistically significant. And then the test scores in the two groups are also very similar. So we get that the average test score in the treatment group was 72 at 0.2, and the average test score in the control group was 72.7. So these are also not statistically different. So what does that mean? That means, did randomization work well or badly? What do you think? Let me see, there's a chat. No worries. So does randomization work well here? What do you think? Does a treatment and control group look the same, or do they look different? If randomization worked, the treatment and the control group should really be about the same in most categories. Leanna, Kimberly, Katrina, Ibrahim, Esmeralda, Devin, Derek, Cameron. Yep. Okay, good. So they do look the same. They look the same. What's this? They look the same. Therefore, it looks like randomization worked. Okay. What kind of p-value should we be concerned about? When the p-value is less than 0.05, we should be worried. Okay. When the p-value is less than 0.05, we should be worried. Okay. So here are some values. So these are, I think, from the real study. So we see that in the treatment group, we started with achievement of 72. And then after treatment, a year later, they had achievement of 78. So their achievement is going up by 6.27. In the control group, so what's the problem here? We want to know how much of this would have occurred anyway if they hadn't been treated. So we're going to use the control group, and we're going to look at how did their achievement change in the absence of treatment. And here we find that achievement, even in the control group, is going to go up by some, and it's going to go up by about 1.8, almost 2. Okay, so we can, and maybe we should just do this, we can generate all of the betas of a normal regression using this table. So what is the beta naught? The beta naught is the omitted category. So the omitted category here is control, because we have an indicator for treatment, before, because we have an indicator for after. It's just the only group that hasn't been called out in the regression. So that's why we get that let me clear this. So the beta naught will be the omitted category, which is why these values are exactly the same. Okay. I'm going to try to do this really slow. Treatment, the coefficient on treatment. So why is that? Because that is the value of the omitted category. So that's just important, is that the beta naught is always the average value of the omitted category. Okay, we've gone through that a couple times in different ways, but that's important. So how do we calculate this negative 0.591? Then the coefficient on treatment is the difference in outcomes before treatment or the pre-existing difference between treatment and control. So we're going to use this value right here, which is just the difference before treatment happens. That will always be the coefficient on treat. Okay. So if this doesn't click, you break in, let me know, because this is fun and it's important. So what's the variable? What's the coefficient on after? The coefficient on after is the difference in outcomes in the control group over time. So to find that, we're going to take 74.6 minus 72.751, and we're going to find that it's this value right here. So that's where this comes from. Okay. And then the last thing is, I'm trying to find a color that I can use. Let me find a color. So the coefficient on the treatment after interaction term is the difference in difference estimate. So what we're doing is we're taking these two differences here. So this is the first difference, the difference before and after in the treated group, the difference before and after in the control group, and we're taking the difference between those two. So 6.27 minus 1.87 is going to be 4.392. So that's where this comes from. So what you should get from this is that if I give you this table right here, you can calculate every single coefficient in the regression. And that would be cool. Okay, questions here? Warren, Yesenia, Stephanie, Noah, Luis, Levi, Leanna, Kimberly. Devin, how you doing? You okay? Looks good. Okay, good question from Leanna. So these, she asked, what are the numbers in parentheses? Can anyone help us here? What are these numbers in parentheses underneath the regression? What are these? You should, I think everyone knows. I think at least half the class knows. These are the standard error of the coefficient. So what do you use these for? If I asked you to calculate the whether this is statistically significant, you would go 0.591 minus 0 divided by 0.845. And you'd get that this is some value less than 1. And so it's therefore it's not significant. From the row, the numbers subtracted, the value, rows and columns. Okay. Warren and Noah, can you say more about what you're, am I missing something? Yeah, so those are just, that's right. These are all differences. So this is the difference between these two. 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 And this is the magical one. This is the difference between these two and also the difference between these two. How do you calculate those numbers in parentheses? You're not going to have to calculate the numbers in parentheses. I will give them to you. Don't worry about calculating those. And don't worry about that. If it's a regression like this, I'm going to say I will give you those values underneath it. So we wouldn't end up using the 3.801 to figure out any of the coefficients. You are not going to use the 3.801 to figure out the coefficients. You can, there's a way to use the 3.801 to get these estimates because they're all connected, they're all differences of each other. But I think that the most intuitive way to get the coefficients from this table is the one that I said before. But you could use 3.801 and you could get them back logically. I haven't really thought about how to do that, but it's possible for sure. Okay, questions here? Good question. Good question about the parentheses. Good question about the columns and the rows. Good question about how to get this stuff in parentheses. Okay, sounds good. Okay, so did the deworming, this is a great example of something we might see on the test. Did the deworming pill have a statistically significant effect on test scores at the 95% confidence level? So which coefficient is the effect of the treatment? It is usually R beta 3, which is our coefficient on on the interaction term treat times after. And to get the t statistic to test whether it's significant, we're going to do 4.3 0.39 divided by 1.24. That's going to give us a number that's pretty close to 3, which is greater than 2. Therefore, it's significant. Why did we include the treat variable in the regression? So this is a great question. Why are we controlling for treat? What it does is it controls for differences in the outcome that were present before the intervention. Okay, does that make sense? Was there a significant change in test scores for the control group over time? So if you were asked that, you could look at this after. Remember, the after coefficient is how test scores are changing for the control group over time. And we would learn here that there was an increase of 1.87, so that's kind of big relative to this treatment effect over here. And we can test whether it's statistically significant like so. And here we're going to get some number that's greater than 2. And therefore, it is a significant increase in the test scores, even of the control group. Should we be concerned about omitted variables? What do you think? Yes or no? Nope. We don't have to be concerned about omitted variables. We did random assignment. We checked to make sure that random assignment worked. And because random assignment appears to work, we don't have any variables that are correlated with treatment. We don't, that might affect the outcome variable. So we don't think that there is any problem from omitted variables. Let me pause here. Any questions about that? Okay. So what problems could there be with this study? The major problem with experiments like this is that if people drop out of the treatment and control group at different rates, there could be a big problem. So say, I think that would be very common, say the control group starts dropping out of the study because they didn't get a treatment. So they are miffed, they didn't get anything out of this research, and so they start leaving at a different rate than the treatment group leaves. Well, then we're going to have a comparison group, a control group that's not truly similar to the treatment group. Another version of attrition would be if the death rates were different between the two groups, if the control or treatment group are moving to a new city at a different rate, if some group, either the treatment or the control group, are more likely to not want to respond to follow-up surveys, or if people that weren't treated are less likely to attend school. So you can imagine the deworming thing makes it easier to go to school because your feet don't hurt. Maybe it's harder to see the people who we didn't deworm because they're less likely to show up at school. So if these things occur at different rates for the two groups, then our groups will no longer be comparable or balanced. So we usually check to make sure that the same number of people attrit in the treatment and the control group, and check for balance in the after period. So we might say after the treatment has taken place, do we still find that there are about as many males in the treatment and the control group, etc. Any questions here? Kimberly, Leanna, Levi, Luis. Okay, so this is pretty cool. I think you're going to like this bit. So a natural experiment is, these experiments are really hard to run. You've got to go out, convince a bunch of people to let you randomly assign them to different things. You got to raise a bunch of money, usually millions and millions of dollars. So often we're looking for natural experiments because we don't have time or the resources to randomize everything. And a natural experiment is a treatment and control study where the treatment and control are not explicitly randomized or intended to be randomized for the purpose of research. So these experiments, these scare quotes are because they're not literally randomized usually, are due to policy changes or other phenomena. So sometimes there's a smoking ban, a minimum wage change in one state and not another, or a change in trade policy. So these can all form a kind of natural experiment where we haven't literally randomly assigned things, but we can try to approximate a randomized experiment. So why are natural experiments cool? Well, if you're budget conscious, these are great. So they're inexpensive. You don't need to go out and randomly assign everybody to different treatments. And you can answer big, important questions that are actually already going on. So often you're going to be looking at something that's already happened. So it's kind of, in some sense, it's an important thing to do because people are already trying to do it. So it's good to have more information about whether this is a good thing or what the consequences, the benefits and the costs might be to a certain kind of policy. The limitations to a natural experiment are that there might not be random assignment to the treatment and the control group. So that can be a bummer. And we might also be concerned, because of it, we might be concerned about omitted variables problems. So we'll talk about that a little bit more in the next slide. So what I think you should know is how to set up the equation, how to do a difference in difference, how to interpret the results, and understand the pros and the cons of different research design. So I might say, what's the downside of an experiment? What's the downside of a natural experiment? What's that would be kind of a natural thing to ask. Okay, so this is a great example of a natural experiment that we've actually talked about already in this class. We're interested in studying whether charter schools might be better or worse than regular government schools. And we don't just want to compare kids that chose a charter school to kids that chose a government school, because the kids that choose charter school might be different. They might be more motivated. They might have parents that are more on their case, or there might be all sorts of differences that make a simple comparison of government school students and charter school students different. So what can we do? The thing that has been done, which is pretty cool, is that charter schools usually run their admissions via lottery. So when they have too many applicants and not enough seats, they say everyone that wants to go in will be put into a lottery, and we will just randomly draw who gets into the charter school and who doesn't. So the useful thing about that is that if we compare the kids that were randomly admitted to charter schools to the applicants who were randomly rejected, they're going to be the same in all of their observables and the same in all of their unobservables. And so these make great treatment and control groups. It's as if they worked as a randomized control trial, like a medical trial, but it just happened that this was done for sort of another reason, which was to allocate scarce seats in great schools to students. So what we'll do is something like this, where we'll just do a regression, a difference in difference, where we have test scores for the kids before and after they applied to a charter school. We have whether they were awarded a seat at the charter school in the lottery, whether we're observing them before or after the lottery that they enroll in the charter school. And then we have this interaction term, and the coefficient on the interaction term gives us the effect of attending a charter school on your test scores. So that's kind of the basic motion of this kind of natural experiment. It's a nice natural experiment because it literally looks like an experiment. There's random assignment, whether you get the treatment or not. Okay, let me take questions. How do you guys feel? Could you give me thumbs up, thumbs crossed, thumbs down in chat so I know whether this is like feels good, doesn't feel good? Is there a thumbs down motion? Let's see. Well, there's not a thumbs down, I guess. But okay, so most people have thumbs up, it looks like. Awesome. Okay, cool. I am going to, I will ask you a very high level question on this deck, I think. A question that if you kind of were paying attention in the class, you would definitely know. So we've been talking about endogeneity, and we have a couple ways of dealing with endogeneity. We can use differences in differences. We can use experiments. What we're going to talk about right now is a thing called instrumental variables. Instruments, and instruments is another way of addressing omitted variables bias and simultaneity. Okay. And basically what instrumental variables is when we find a variable that's correlated with the X that we think is problematic. I'm sorry, let me just handle my kid really quick. Okay. So we get biased estimates when we have omitted variables, when we have reverse causality, and when we have measurement error. And instrumental variables is one of the things that we can do to address it. So, so this is how we're going to go through this today. I'll re-examine omitted variables with you. This will look very kind of at home. And then I'll talk about what instrumental variables do in theory and a couple examples of in instrumental variables. So by now, you're probably tired of me saying instrumental variables without knowing what they are. But the key is first to understand what the problem is that they're solving. So imagine that we are interested in the effect of skipping class on your scores at the end of a course. And so if we did a simple regression where we're just regressing your kind of the score at the end of the class on how many times you missed class, what sign would we expect beta 1 to have? Positive or negative or 0? We probably think that beta 1 is going to be negative. That means that as someone misses more and more classes, that their score on the final exam might be lower and lower. Do we think that the beta 1 that we estimate in this regression is causal? Probably not. Why? Because there are omitted variables. So there are variables out here in the error term that are correlated with skipping that also affect your test score. So what could those be? I think a really natural one would just be motivation. Perfect, yes. Personal issues. So that would be a prime one that you've got, or health problems. Motivation, so just how much do you care about your school is going to affect both how many times you skip a class and how much you're studying, and therefore what scores you're going to get. Whether you've got work, and so all of these different things are going to affect, all of these different X's are going to affect whether you skip, and then also your scores. So, and thanks for those. Those are great. Those are great examples of omitted variables. Okay. Okay. So the one that we're going to consider first is just motivation. So it's just, let's imagine that you're all healthy and you've got no family stuff going on. It's probably safe to assume that motivation is positively correlated with your scores. So if you really care about your schoolwork, you're going to have higher scores, and it's negatively correlated with the number of times that you skip. So if you really are motivated in your schoolwork, you're going to maybe skip fewer times. So what does that mean? It means that beta 2 is positive and delta 1 is negative. And so the beta that we estimate is going to be smaller than the true beta, because this term here is a positive value times a negative value, which is a negative value. Okay. So the estimated effect of skipping class will be downward biased when we omit motivation. Our estimate of beta 2 will be too negative. So we're going to overestimate how bad it is to skip, because some of the people that are skipping just don't care. Okay. And that would be true of a lot of the other potential omitted variables that you all contributed. So this is maybe what we find when we do a simple regression. We have that the typical score for someone that missed no classes would be 84.3. And then for every day you skip, your score goes down on average by 2.8. Okay. So we can test the hypothesis that the number of skipped classes has no relationship with your test scores by taking the coefficient on skipped and dividing it by the standard error of that estimate. So we would say negative 2.82 divided by 0.75, and we'll find that that is 3.75. That's bigger than 2, so it's statistically significant. Okay. So we reject that skipping class has no relationship with your final score, but this might be too big. It might be too big of an effect because of omitted variables bias. It might be an effect that's larger than the true effect. So one solution is to find an instrumental variable. So this is going to sound like magic. I just want you to think about this as a kind of cool magic. The instrumental variable is a variable that has two properties. One is that it's correlated with the explanatory variable that we're interested in. So here, that's whether you skipped or not. Two is it's a variable that's uncorrelated with your error term. So we're interested in finding a variable that is not related to anything else that affects your test score. So it's not correlated with motivation in our example. So one proposed instrument might be how far your dorm is from the classroom. So you can imagine if your dorm is really far, like so UC Merced is a little different because it's a smaller campus. But if you're on a campus with 30,000 students and you're spread over miles and not acres, you are much more likely to miss a class just because you're so far away. So if your foot hurts, you can't get all the way across campus. If you sleep in a little bit, you're just going to be too late to make most of class. So if distance is correlated with skipping and it's uncorrelated with motivation, then we can use it to estimate beta 1 without any bias. So that's the magic, is that by finding a variable that is correlated with skipping, that's not correlated with motivation, we can estimate the variable. That is a great idea, Katrina. So whether you have rain on a particular day or whether a particular semester is pretty rainy would be a great instrument as well. That's a very good idea. Yes, thank you. Okay, questions. Questions. Devin, Derek, Cameron, Esmeralda, Ibrahim, Katrina, Kimberly, Leanna, Levi. Any questions? No response at all. No response. Are you out there? Are you listening? I can see a couple of you. How are you doing, Ibrahim? Are you okay? Sounds good.
Good, Professor. How about yourself?
No, I see. I see it. You're doing great. Yes. Okay. Okay. So we want to see what an instrumental variable is actually doing. So let me just review a couple of the properties of covariance. So remember that when we take the covariance between x and any constant, it's 0 because a constant can't covary with anything because it's never varying. So it's the covariance between x and a constant is 0. The covariance between x and itself is just the variance of x. And when we take covariance of a times x with some y, we'll find that that's equivalent to a times the original covariance of x and y. And then finally is if we take the covariance of x with the sum of two variables, we find that you could actually just split that up into the covariance of x in one variable plus the covariance of x plus the other variable. So you don't, let me see, some of these were on the midterm. So this was on the midterm, this was on the midterm. I even think this was on the midterm, maybe. I can't remember. Oh, that's weird. How did that happen? That was weird. See how it's like ribbony? I don't even know how I did that. Okay. So we want an unbiased estimate of the following regression. Y is some function of x. And first, we're going to show that the ordinary least squares of that is going to be biased if x is correlated with the error. And then I'm going to show you that if we get an unbiased estimate if we have an instrument that satisfies the two properties. The first property is that the covariance between x and z is not 0, and so that means that there is a correlation between x and z. And then second is that the z is not correlated with the error term. If we have those two things, we can get an unbiased estimate of beta 1. So first, we're interested in the correlation between x and y, and we're going to plug in for y this value right here. So remember, we always have these regressions where y is equal to beta naught plus beta 1 x plus u. Okay, so we can plug this in for y. And then we can break this up. So remember, when we have the covariance between x and a sum of different things, we can break these up into different covariances. We have the covariance of x and beta, we have the covariance of x and beta 1 times x, and we have the covariance of x and u. And so there are two things to see here. One is that this is going to go to 0 because beta 1 is a constant. It's a constant, so that's going to go to 0. This, we can just take the beta 1 out of the covariance and bring it to the front. And then just remember here that we have the covariance between x and u. What we're basically saying is, say we know that x and u are correlated. So this is not going to be 0. Okay, so there's going to be a problem for bias. So when we do all that, we're going to end up with the covariance of x and y will be beta times the variance of x plus the covariance of x and y, which is not equal to 0. Okay. So what will we be left with when we are calculating our beta 1? We will have some true beta 1 plus the relationship between covariance and u divided by the x. So basically, this right here won't go away, and we'll have this will be the bias term. That will reflect how far off our estimate of beta is from the true beta. Okay. So why is that? It's just because the x's are the x is correlated with motivation. So here our skipped is correlated with motivation. More generally, so that the x that we're interested in is correlated with the error term. Okay. So let's do the instrumental variable version. We're going to calculate what is the relationship, what's the covariance between x and y. And so we're going to do the exact same kind of math where we've got, we're going to take for y this, and we're going to break it into chunks. And here we've assumed two things. Well, first, this is not an assumption. This is equal to 0 because beta 1 is a constant again. And this is equal to 0 because we've found a good instrument that's not correlated with the error term. So in our example, that it's to assume that distance of your dorm from your class site is not correlated with your motivation. Okay, so the result is that the covariance between z and y is going to be the same as the correlation between as beta 1 times the covariance between z and x. And that's just flowing through from here. Remember, the beta 1 comes out. So what we find is that when we take the covariance between x and z and y, and we divide it by the covariance between z and x, we'll get the true beta 1. There won't be a bias term. Look, Mom, no bias term, because the correlation between z and u is 0. So one way to think about this is the following. So skipping has two parts. Skipping has a part which is endogenous, which is if you're less motivated, you're skipping more. And it has a part which is exogenous. It's not related to anything in the error term. It's whether it's raining, it's how far you live from, how far your assigned dorm is from the classroom, etc. And what the instrument does is it uses only the variation in x that's coming from distance from your room, distance from your dormitory. So that's kind of the logic of it, is that you're using the part of the variation in x that's unrelated to other things. Okay. So I don't want you to worry about this math that much. I'm just showing you where the math comes from and what it implies. It implies that the beta 1 that we get with an instrument, if it's a good instrument, will be unbiased. Okay. So the summary, what is the summary? Is that least squares will be biased because x is correlated with the error term, but an instrumental variable estimate will not be biased because the z that we choose is not correlated with the error term. And so we get an estimate like this. The beta IV is the covariance between the z and the outcome divided by the covariance between the z and the x. So this is very similar to our normal estimate of beta 1, which is the covariance of x and y divided by the variance of x, except that z is substituted for x. So the numerator is measuring how much the outcome variable changes with z, and the denominator measures how much the explanatory variable changes with z. So basically what we're saying is there's this much change in the outcome variable for a given change in x, and then we're dividing that how much change in x is there for a given change in z. And so it's the same kind of principle that we had before, where that's the rise, the change in y for a change in z, over the run, the change in x for a change in z. So that's what gives us this slope parameter, which is the slope is the rise over the run. Okay, there's got to be questions. Cameron, Dennison, Devin, Esmeralda, Ibrahim, Katrina, Kimberly, Okay, sounds good. Oh, cool. You might have seen this in another class. I'm not sure where. If any of you have taken Ketke's class in development economics, she does a lot of this. It's very, she would probably do it in her class on development and probably in her class on applied econometrics. Oh, maybe math 32. I don't know. That's great. So we think that distance from the dorm is a nice instrument. Do we think that one is likely to hold, where one is the claim that distance is correlated with skipping? Do we think that distance is correlated with skipping? Yes or no? What do you guys think? Is how far your dorm is from the classroom correlated with how often you might miss a class? Obviously not during Zoom, but yeah. Yes. Okay. So the one cool thing is I kind of think yes. I think that like it will have a small effect on how many times you miss class. But the great thing is that we can test it. We can actually run a regression where we run a regression of skipped on distance. Okay. And if this value is not equal to 0, then we know that the distance is correlated with the explanatory variable skipping. That's kind of cool. So do we think that the second condition is likely to hold, which is that it's uncorrelated with the error term? So do we think that distance between your dorm room and the class is correlated with your motivation in this example? Do we think that's true? No. We think that people that live closer to their classes might have different motivation levels. So I could see a case that, especially if you're living wherever you want to live, that might not be true. You could imagine a setting in which your dorm rooms are assigned. So you put in that you want a dorm, and they say, "Great, we've got a room in Grennan Hall," and the Grennan Hall is located here. So they're like at West Point, they randomly assign what dorm you're in, who your roommate is, all of that is randomly assigned. So the bummer is that it's very difficult to test whether our instrument is correlated with the error term. So that's kind of the bummer about instrumental variables, is that they're hard to test whether they're actually solving the problem. So we can test the instrument, see whether it's correlated with our explanatory variable skipped, something like this. And we can test whether this relationship is statistically significant by dividing the coefficient by the standard error of the coefficient. So that's where we get this. And we're going to get a value of 2.8, which is larger than 2. So it is significant. What does that mean? It means that the instrument is correlated with the explanatory variable. So I might ask, oh, how can you test, how could you test? I think this is the most likely question for instrumental variables. What is a good instrument? And the answer would be, a good instrument is a variable that is correlated with the x that you're interested in, but not correlated with the error term. So that's what a good instrument is. That's probably what I'll ask you on the test. Another thing I could ask you is, how could we test whether the instrument is related to the x variable? And you would just say, I would run the x variable, I would run a regression of the x variable we're interested in on the proposed instrument. So here we're regressing skipped on distance. That's what we're doing. Okay, questions? Okay, so this is the estimate based on, so this is basically what we would get if we use that as the instrument. So we get that skipping has a negative effect, but actually it's a much smaller negative effect than we had before. I think that before we had something like we had something like negative 2.8. I can't remember exactly, but you can see that 1.4 is much smaller. So we can see that this is smaller in magnitude and it's not statistically significant. How do we know? Because we can divide 1.43 by 1.12 and find that that is going to be a little bit over 1.3 or something like that, which is less than 2, so it's not significant. So when we use an instrumental variable, we find that the effect of skipping class is smaller in magnitude than when we just use ordinary least squares. This is probably because of omitted variables in our OLS estimate, like motivation or having to work, things like that. Okay. So here's the summary for today, and then I'll just show you a few kind of cool examples of instruments that people use, and we'll talk about whether they make sense or not. So we're concerned that our explanatory variable is correlated with the error term because of some omitted variable that we don't know. And what we want to do is find an instrumental variable that's correlated with the explanatory variable, but not correlated with the error terms that we're worried about. And then we'll estimate beta 1 using the instrumental variable and compare it to the least squared regression. So if our instrument is a good one, then we have fixed the omitted variables problem, and it is a little bit like magic because we're using the part of the variation that is not contaminated by omitted variables bias. So let me see here. So we're concerned about ability. So, I'm not going to do this one because I think this will confuse. It's not a good instrument, but let's just talk about a couple famous instruments. One that's kind of related to what we've been talking about today is that they've used whether you attend. We're interested in the effect of attending college on outcomes. Well, sometimes people have used how far your high school is from a college as an instrument on whether you attend. So you can imagine if you live in a college town or you live in a town with a community college, you might be more likely to attend that college because it's not very costly to go. You could stay at home, and we can use distance to college as an instrument on whether you attend. A really fun series of papers uses the Vietnam War draft. So in Vietnam, we were still drafting people into the wars. And what was interesting is that they did it on television, and they said, we have every birthday in a big lottery machine. So they have all these like little ping pong balls with different birthdays on them. And if we pull your birthday out of this lottery machine and it's your birthday, you have to go into the US military to fight in Vietnam. So what's great about that is that whether you went to war in Vietnam is essentially randomly influenced by this draft lottery. So if we were interested in the effect of military service on your college attainment or your labor market outcomes, people have used whether your birthday was one of the birthdays drawn in Vietnam. And then here's another interesting instrument is that whether someone immigrates to the U.S. is endogenous. So people immigrate because they're making a choice. But what we sometimes want to know is, well, what's the effect of immigration on local outcomes, local wages, or local employment? What people have done is they say, oh, well, actually, we know that there's a lot of immigration when there is a drought in Guatemala or a drought in Mexico. So we can use the rainfall in Guatemala as an instrument on when people immigrate to the United States. That's these are kind of different things. They're all correlated with, each is correlated with the variable that it's interested in. And we think that these things have a kind of random quality to them. Being born near a college is not kind of your choice, but it has an effect on your college attendance. Having your birthday randomly drawn in a lottery isn't your choice, but it affects your military service. And whether it's a rainy year or not in Guatemala affects immigration, but it's not correlated with the other things that might be shaping your decision to move. So that is all I have for today. I'm sure, why don't I take questions about this material and any material that you've been studying and puzzling about, and classes dismissed, and I will see you guys on our last day tomorrow. I'm kind of bummed about it, but I will make it through, and very good luck studying for the exam. Just as a reminder, we have the exam on Monday at 10 a.m. in this Zoom link. We will have a review session tomorrow in the second half of class. We will also have a review session on Friday morning at 9 a.m. in this Zoom link. And I uploaded about a dozen kind of sample questions that were basically lifted from the exam. They're free response, so I want you to use it as a study guide. I want you to go through and answer those questions as best you can. Check them with other people, check them with me in the review period, either tomorrow or on Friday, and use it as a study reference. That would be a really good use of your time. And I think the study guide is just useful. You can read those questions and think, oh, I got this, I can do these, or I'm not sure about how to do some of these. And that will kind of give you a guide about the intensity that you need to study and the topics that you need to study. Okay, so class is dismissed. And yep, my pleasure, Yesenia. You too, Daniel. Derek, I'm sorry. My pleasure.